civilpe.net.
Alright, we're going to take our concrete design skills one step further and complicate things a little bit. Instead of a rectangular beam, today we're going to design a T-beam section. Now this example will walk us through the design of a concrete T-beam with the depth of the compression block A less than the depth of the flange. And I'll show you what I mean by that in a little bit. So what we have is a concrete T-beam. The width of the flange is 24 inches. The depth of the flange is 4 inches. The overall height of this beam is 24 inches, and the width of the web is 12 inches. This beam is reinforced with 3 number 6 bottom bars. It's got 2 number 4 top bars and number 4 stirrups at 12 inches on center. Now to change things up a little bit, the concrete strength for this beam is 4,000 psi, and the yield stress for the steel reinforcement is still going to be 60 ksi. What we want to do is determine the moment capacity phi mn of the section. Now our assumptions are exactly the same as they have been all along. Plane sections remain plane, the maximum concrete strain at the extreme compression fiber is 0.003, the tensile strength of concrete is neglected, and once again we are going to ignore compression steel in the compression zone. So now let's start again by constructing our old friends, the stress and strain diagrams. These look exactly the same as they did before. The strain in concrete at the extreme compression fiber at failure is 0.003. We've got the strain of our tensile steel down here. Plane sections remain plane, so this is a linear relationship. C is our depth from our extreme compression fiber to the neutral axis, and D is the depth from the extreme compression fiber down to the centroid of our steel. Our stress diagram once again is the same. A is the depth of the Whitney stress block. C is the resultant force from this compressive stress on that rectangular portion of concrete. And T is the tensile force, which is the area of steel times the stress in that steel. Once again, I've included this section to kind of make things a little bit easier, or to depict things a little bit better, but this is showing the compression zone in our section. Right now I'm showing that A, the depth of our Whitney stress block, is less than the thickness of the flange, and we're going to confirm that in a little bit. So this is the compression zone. So first, let's go ahead and calculate D. D is the same as it was before. It's going to be the overall height of the section minus the clear spacing minus the diameter of our stirrups minus the diameter of the reinforcement divided by 2. Substitute in our values and you get a D of 21.625 inches. So now that we calculated that D, we're going to use equilibrium to solve for A, the depth of the Whitney stress block. So from the rules of equilibrium, we know that C, the compression force, must equal T, the tensile force. But first, let's make a quick check. This is a quick check I like to make in order to check whether or not A is less than the thickness of the flange. So what we're going to do is we're going to set A equal to the thickness of the flange and calculate the compression force C and compare it to the tensile force T. Now what this is going to tell us is if we make this calculation and the compression force C is greater than the tensile force T, that means that our A, the depth of our Whitney stress block, has got to be less than the thickness of the flange. Now contrary to that, if our compression force C is less than the tensile force T, that means that A is going to have to be greater than the thickness of the flange, and we're going to have to vary up our calculations a little bit. So for our calculation, we've got the compression force is equal to 0.85 times F prime C times the width of the flange times the thickness of the flange. So that equals 0.85 times 4 ksi times 24 inches times 4 inches, or 326.4 kips. Our tensile force is equal to our area of steel, which is 3 times 0.44 inches squared. We've got the 3 number 6 bars, times the yield stress, 60 ksi. Once again, we're assuming that the steel yields here. And we come out with a tensile force of 79.2 kips. This tells me that because C is greater than T, the depth of our Whitney stress block has got to be less than the thickness of the flange. So the calculations for this T-beam will now resemble those of a rectangular beam with B equals to 24 inches. And you'll see that in a little bit. So our compressive force is going to be 0.85 times F prime C times B times A, where B is the width of the flange, that 24 inches. And A is the depth of our Whitney stress block. Once again, this is that Whitney stress block approximation that ACI allows for ACI will let you do more rigorous calculations if you prefer, but this is the method that they have chosen for engineers when they're designing concrete. So we substitute everything in and we get our compressive force is equal to 81,600 pounds per inch times A. We calculated this once before already, but I'm going to run through it one more time. T is equal to the stress in the steel times the area of the steel, and we're assuming that the steel yields before failure. So we're assuming that F sub S equals F sub Y. So if we calculate that out, we get our tensile force equals 79,200 pounds. So now we solve for A. A, by setting C equal to T. So 81,600 pounds per inch times A is equal to 79,200 pounds, and A is equal to 0.971 inches. And as a quick check, we realize that this is in fact less than the thickness of the flange, which equals 4 inches, so our calculations are correct thus far. So now that we know the depth of that stress block, we can calculate C using that equation A equals beta 1 times C. And once again, beta 1 is that factor that relates A to C based on the concrete strength. So for a 4,000 psi concrete, we calculate out beta and get 0.85. Using that beta, we plug it into the equation and we get a C equal to 1.14 inches. So with C, we can finally calculate the strain in the extreme tensile steel using similar triangles. Once again, this equation is showing that C divided by the strain in the concrete, that smaller triangle right there, is equal to this really large triangle, which is D divided by the strain in the steel plus the strain in the concrete. So let's rearrange this equation, plug in our values, and calculate the strain in our steel. And we get 0.054. So now we determine if our section is tension controlled. And a tension controlled section is a section that has a strain greater than 0.005 in the extreme layer of steel. Our strain is 0.054, which is 10 times greater than that strain, so we are extremely tension controlled. So we can assume that phi is equal to 0.9. So once again, we can check to see that the strain yields, or that the steel yields as we assumed. Like I've mentioned in previous videos, we've pretty much committed to memory now that for 60 KSI steel, it yields at a strain greater than 0.00207. Our strain is 0.054, so we already know that it yields, but let's run through this one more time. So per Young's modulus, Young's modulus is equal to the stress divided by the strain. So if we want to solve for the yield strain, it's basically the stress in the steel, 60 KSI, divided by Young's modulus, 29,000 KSI, or 0.00207. And like I said before, 0.054 is greater than that. So our assumption is correct. F sub S is equal to F sub Y because our steel does yield prior to failure. Now let's again determine if the beam section satisfies the minimum steel requirements of ACI. AS min equals 3 times the square root of F prime C over F sub Y times BW times D, greater than or equal to 200 over F sub Y times BW times D. Now I want to bring this up again because here we've got this BW. We've got a T section right now. So what we want to plug in here is the width of the web and not the width of the flange. I also want to use this time to illustrate that if you get a stress in your a compressive strength of your concrete less than 4,500 psi, this equation ends up controlling. So for us, our AS min is equal to 3 times the square root of 4,000 psi over 60,000 psi times 12 inches times 21.625 inches, which is D, greater than or equal to 200 over 60,000 psi times 12 inches times 21.625 inches. What that comes out to is this equation yields 0.82 inches squared, whereas this equation yields 0.87 inches squared, and 0.87 inches squared ends up controlling. What we have is 1.32 inches squared, which is greater than this 0.87 inches squared, so therefore we satisfy the minimum steel requirement. So using moment equilibrium, let's calculate the moment capacity of the section. So we're going to calculate the moment capacity about the center of the compressive force and determine that moment capacity. So if you calculate the moment about this point, the center of that compressive force, you once again get that the moment, the phi mn, is equal to phi times the tension force times its moment arm, which is d minus a over 2. Looks familiar. It looks exactly the same way as it did when we had a rectangular concrete beam. So you calculate that out and you get phi mn is equal to 1,507 kip inches, which is equal to 122.6 kip feet. So basically I just wanted to illustrate that with a T-beam section, as long as A, the depth of your compression of your compressive block, of your Whitney stress block, is less than the thickness of the flange, there's no difference in your calculation between a rectangular concrete beam and a T concrete beam. So if you have any questions or comments on this video, send me an email at info@civilpe.net. Check us out on the web at www.civilpe.net.